absolute and conditional convergence, otherwise called AC and CC. We have the definition of AC and CC. A series is absolutely convergent if, when you put absolute values on all the terms you're adding up, you still have a convergent series. In this situation, the given series is AC. How about the definition of CC, conditional convergence? In a series which is conditionally convergent, the series itself does converge, but when you put absolute values on all the terms that you're adding up, you result in a series which diverges. So a series which is conditionally convergent relies on somehow terms canceling out. This leads to a grading of convergence, that we have strong convergence in an AC, and we have a weaker type of convergence in a series which is CC. There is a theorem that tells us absolute convergence implies convergence itself. That seems pretty obvious, but it's nice to go through the proof and see how it's done. If we have a series which we know is absolutely convergent, does the series itself converge? The proof shows us that we can write the series in terms of two convergent series, and therefore itself converges. So absolute convergence implies regular convergence. Okay, that's good to know. Some examples. We have example 521. Two different series are considered. In the first series, we can see that it is alternating, and it's something like the alternating harmonic series. The fact that it alternates will lend itself to converging, but the fact that it's like the alternating harmonic series tells us that it is absolutely divergent. With the series itself converging, but absolutely diverging, we have that series is conditionally convergent. How about part B? In part B, we're taking cosine as a numerator. Cosine can be positive valued, can be negative valued, but the size of cosine is always less than or equal to 1. Therefore, our given series is like a p series with p equaling 2. Hence, the fact that cosine alternates between positive and negative values doesn't contribute to convergence of the actual series. And in fact, if we throw away the pluses and minuses, we find that the series still does converge. Hence, the given series is absolutely convergent. All right, so in A, it's like the alternating harmonic, i.e. it's conditionally convergent, and in B, it's like a p series with p equaling 2, so it has no trouble absolutely converging. Now, why is this so interesting? Why is it nice to be able to grade strong convergence and weaker convergence? What's the big deal? In example 522, we have a nice rearrangement example. It starts out by stating that the alternating harmonic series converges to a nice value. They then walk through looking at a rearrangement of these terms. And in that rearrangement, they show that using all of these terms, but ordered in a different fashion, it produces a completely different value. This is the alternating harmonic series, which is conditionally convergent. And if you take things in the given order, it will converge to this value. However, if you blink at this thing, it will somehow produce a different value. Hence, we have this notion of convergence, which you can rely upon, you can take to the bank, quote unquote, and then you have another type of convergence, which may do strange things. Very nice.